Hello, this is John Kavanagh from D&V Software, and it's a quick guide to setting up your own analysis in Phast 7. The main aim of the analysis is to show you how you can define equipment and scenarios to represent the most common types of hazardous event, and how to take into account the main variables. To create a new workspace, if you have the example file open, you can select either Close or New Workspace Phast from the File tab. This will open a new workspace. You cannot save the workspace with the name workspace, so you should save it with a real name immediately. Go to File, Save As, and then save the file with the name Tutorials. The new workspace will not be empty, but will have some default data set up. The weather folder will contain 3 weathers, and there will be a set of default parameters also set up. We will now set up the map image. The tutorial uses a map of an area near 2 rivers in a country which has a national grid system. The image for this map is supplied within the program in the form of a TIFF file. If you have an image file for the area around your facility, you might prefer to use that instead. So to insert the raster image file, you first go to the Maps tab section. Ensure that there is a raster image set in the Map tab section. If the Map tab section of the study tree does not already contain a raster image set icon, select the tutorial icon at the top of the tab section and use the insert option in the right click menu to insert a set. The set is a folder for raster images, and you have to insert raster images inside the folder. Select the raster image set, and then from the right click menu select Insert Raster Image. A dialog will appear, and you must first browse to locate the image file. The tutorial.tif file is located in the examples file inside the Phast program. When you first browse this folder, you may not see any files in the list of file types, as it is not set to TIFF by default, which you may have to do. When you have selected a valid raster image file, the placement mode fields will become enabled. These are options for specifying the map coordinates covered by the image. Some files contain georeference data or header data that you can use to set the coordinate data for the image, but the tutorial file does not, and the only option available is the interactive option, which is available for any raster image file. When you click OK on the Insert dialog, the GIS input view will become selected if it is not selected already, and will display the instructions. Drag a box to define the raster image size and location inside the view. The cursor will be in the form of a crosshair, and you must drag and drop to place the image in the view. This sets the initial values for the map coordinates for the image, which you will set to the correct values in the next step. A tutorial icon will now be present under the raster image set. Double click on this icon to open the input dialog for the image. Move to the Geometry tab section and set the values of the coordinates of 196855 east and 436053 north, with a width of 4489 and a length of 3570. When you click on OK, the image will probably disappear from the GIS view because it has moved to a location beyond the scope of the view. To make it visible, click on the GIS input view in the ribbon bar, and then click on Fit All in the General tabs of this group. The GIS view will change to display the area covered by the image. For the tutorial, the facilities occupies the long narrow section of the land to the north and west of the village, between the east bank of the river and the road that runs parallel to the river, shown shaded yellow in the illustration. We will now perform the consequence analysis. Firstly, you need to define the pressure vessel that contains a toxic material. So move to the Models tab section, and you will start by defining the pressure vessel equipment item that contains a toxic material. The vessel is a sphere with a radius of 3.37 meters and volume of 120 meters cubed, and a maximum fill level of 85%, containing chlorine at saturation conditions and ambient temperature. The sphere is located near the centre of the site and is elevated 4 meters above the ground. There is no bund surrounding the sphere. So firstly, you must turn on the option to insert equipment on the GIS. So in the Tools tab of the ribbon bar, check the option to insert equipment on GIS. By default, this option is turned off, and when you insert an equipment item, the icon will appear immediately in the study tree. If you turn the option on, then the equipment icon will not appear in the study tree until you have clicked on the GIS input view to set the location of the equipment item. In this tutorial, you insert the equipment item on the GIS view in approximately the correct location, and then correct the location as necessary in the input dialog. So firstly, to insert a pressure vessel equipment item, select the study, then on the right click menu, select Insert Pressure Vessel. The GIS input view will become selected. The cursor will turn to crosshairs, and you should click a point near the centre of the site to place the pressure vessel. After you've clicked, an icon will be added to the study tree, and a dot will appear in the GIS view to show the location of the pressure vessel. In the study, rename the node to chlorine saturated 10 degrees C. We must now set the input data for the vessel. The pressure vessel node will have a red error icon at the top left, showing that it does not have a full set of data. You will not be able to run the constants calculations for any scenario under the pressure vessel until you have supplied values for all of the mandatory input fields. So firstly, double click on the pressure vessel to open the input dialog. Most of the fields in the first tab section will be blank, and those that are enabled will have red borders and error icons. A field with a red border is a mandatory field. You must supply a value for each such field if it is enabled, and you will not be able to run the calculations for equipment items or scenarios that have any mandatory fields unset. So to set the material, select chlorine from the drop-down menu. The vessel is a sphere with a volume of 120 meters cubed. This equipment item will represent the vessel with the maximum degree of filling, which is 85%. So check the specify volume inventory and enter a value of 102 meters cubed. The chlorine is held under saturation conditions at atmospheric temperature. The temperature will vary depending on the season and time of day, but for this equipment item, a value of 10 degrees C will be used as a representative. To set these process conditions, set the specified condition to temperature/bubble point and set the temperature to 10 degrees as shown. When you move the cursor away from the temperature field, the program will calculate the saturation pressure for the temperature and display it in the pressure field. After you have set the storage conditions, the phase to be released will be set to liquid, which is the default value. We will now move to the dispersion tab section. The program requires a criterion for stopping the dispersion calculations, either a maximum distance or a minimum concentration. You will set values in the pressure vessel dialog to be used as the defaults for all scenarios under the vessel. For this tutorial, Set the concentration of interest to 100 ppm. When you set this concentration, the average time for concentration of interest field will become enabled and mandatory, as you must specify the average time to be used in the calculation for stopping the dispersion. For a toxic release, the list allows you to choose the toxic averaging time or the time associated with the ERPG, IDLH or STEL measures of toxicity, or to specify a user-defined time. For this release, select the toxic averaging time, which is the set in the toxic parameters and has a default value of 600 seconds. We will now look at the Toxic Parameter tab section. The fields in this tab section are used in modelling the toxic effects for people indoors, in buildings, and in the path of the dispersion cloud. By default, these calculations are not performed, but for this tutorial you should turn them on by checking the option to specify downwind buildings. The calculations require information about the ventilation rate for the representative building and about how long people remain in the building after the cloud has passed and the concentration is lower outdoors than indoors, and this information is designed using the building type node in the Map tab section of the study tree. The new workspace is created with one building type called default building already defined with the ventilation values and evacuation values set to the defaults. This default building type is selected by default, and for this tutorial you should leave the specified downwind building field with this default setting. In the Geometry tab section, set the eastern coordinate to 198492 and the north coordinate to 435063. Now that you have defined the pressure vessel, you can find any number of different scenarios underneath it. The catastrophic rupture scenario is defined here first, as it has the simplest set of input data. So to do this, select the pressure vessel node, and then in the right click menu, select Insert Catastrophic Rupture. We'll now set the input data for the catastrophic rupture. The node will not be shown as incomplete when you insert it, as the catastrophic rupture scenario does not have any mandatory input fields. All the fields take the input default values from the pressure vessel. For this tutorial you will edit scenario and set a non-default value for one field. So firstly, double click on the catastrophic rupture to open the input dialog. The default value for the release elevation is 1 meter, but for the rupture you should set this to 7.37 meters, which is the elevation of the center of the sphere above the ground. You could have set the value of 7.37 meters in the input data for the pressure vessel, but the other scenarios will have different values for the elevation, and to reduce the risk of confusion, the pressure vessel has been left with the default value of 1 meter, and the elevation is being set individually for each scenario. If you look at the dispersion and toxic parameter tab sections, you will see that the values that you see in the pressure vessel dialog are present and shown as default. The setting for the concentration of interest and the indoor toxic modelling are the same for all scenarios for this equipment item, as they are likely to be for most equipment items, so it is appropriate to set the values of the equipment item level. Finally, click OK to close this dialog. We will now run the calculations for the scenario and view the results. Select the scenario and select Run from the ribbon bar. When the calculations are complete, view the graphs for all the weathers. To do this, select the scenario, Then click on the Graphs option in the Home tab of the ribbon bar and select all three weathers in the Select Weather option. You will see that there is no Pool Vaporization tab in the Graphs view, which means that the liquid in the release did not rain out. If you want more information about the behaviour of the liquid droplets in the cloud, you should view either the commentary report or the dispersion report. The concentration graphs only ever show the outdoor concentration, but if you move to the Toxic tab section, you will see that the probit, lethality and dose graphs display separate results for indoor and outdoor effect. The lethality graph shows that the greatest downwind effect distance is for the f1.5 meter per second weather outdoors, with a distance of about 2.5 kilometers to a lethality level of 10%. The indoor effect for this weather reach about 2.25 kilometers to 10% lethality. The shortest downwind effect distance is for the d5 meters per second indoor, which reaches about 1.4 kilometers for a lethality level of 10%. We will now look at viewing the outdoor toxic lethality results against the map. So firstly, select the scenario in the study tree and then click on the GIS button in the Home tab of the ribbon bar. A Select Weathers dialog will appear listing the weathers for which calculation has been performed. And the same as when you view the graphs, make sure that all the weathers are selected and then click on OK. After a pause, a GIS result view will open, appearing as a separate tab in the document view area, which is the area that contains the graph view and the GIS input view. GIS results view display footprint and contour results on the GIS. By default, GIS results view display the cloud footprint results, but if you move to the Consequence tab and go to the Event option, all of the types of footprint and contour results that are available for scenario and weathers covered by the GIS view are available. And you use this list to view a different type of effect. For this tutorial, select the Toxic Outdoor Lethality footprint. If a graph view or GIS results view is displaying results for a single scenario and weather, it will display results for more than one effect level when it first opens. However, if it is displaying results for multiple scenarios or weathers, as is in the case with this example, it will display results for a single effect level when it first opens. By default, the effect level displayed for multiple scenarios or weathers will be the lowest effect level of interest defined for the scenario, which is 0.1% lethality for toxic effects, as shown in the legend. You can change the effect level displayed in GIS Results View by clicking on the Edit Settings button in the Consequence tab. To change the toxic lethality level to 10%, move to the Toxic Parameters tab and enter a value of 0.1 in the lethality levels table. And press Enter. When you click on OK to close the dialog, there will be a pause, and the GIS result view will then display the results for a 10% lethality level. This shows that the effect contours for all weathers are able to reach both the village and the town, although the range of wind directions for which they will be reached is smaller for the 5 meter per second D weather than for the 1.5 meter per second weather. The Edit Settings dialog also allows you to change the number of effect levels to display. By default, this is initially set for one for multiple scenarios or weathers, but you can change that in the dialog. We will now define a second scenario, a liquid release from pipework. So the second scenario we're going to define is a release is from the same chlorine sphere, but the hazardous event is the rupture of a 1-inch liquid line attached to the bottom of the sphere, where the initial liquid head will be 4.6 meters. The line runs 4 meters vertically downwards to 10 centimeters from the ground, then 5 meters horizontally to an isolation valve. The rupture is assumed to occur just before the isolation valve. So firstly, we must insert a time-varying short pipe scenario. There are two types of scenario available for modelling pipework rupture. There's the short pipe scenario, which models the release using the initial release rate for the start of the release, with a duration that is the time required to drain the inventory at this initial rate. This will normally give conservative results in the consequence calculations. There is also the time-varying short pipe scenario, which models the effect of the release on conditions in the vessel and the way that these conditions and the release rate change over time. These time-varying results can be represented either with a single rate or with a series of rates depending on the options that are set for the scenario. So for this tutorial, we will use the time-varying short pipe scenario, perform an initial run of the discharge calculations, and then we will examine the results and decide on the most appropriate way to represent the behaviour for the rest of the consequence analysis. So firstly, to add the scenario, select the pressure vessel. In the right-click menu, select Insert Time-Varying Short Pipe Release, and name this scenario Line Rupture Liquid. We will now set up the input data for the scenario. The new scenario will be shown as incomplete, shown by the red symbol in the top left hand corner. So firstly, we must open the dialog for the new scenario. In the Scenario tab section, make sure the scenario type is set to line rupture. Set the pipe diameter to 25.4 millimeters. The pipe length to 9 meters. The release height from the bottom of the vessel to 0. And the elevation to 0.1. The Scenario tab includes the Outdoor Release Direction field, which you should leave with the default value of horizontal, which is the correct setting for this type of unobstructed rupture of horizontal pipework. The list of directions include a second horizontal option, horizontal impingement. You should select this option if the release is in a congested area and the release is likely to impinge on a wall or other equipment. The program will reduce the momentum of the release, which will reduce the amount of air mixed into the jet during the initial stages. We will now edit some features of the Materials tab section. When the vessel to which the scenario belongs contains saturated liquid, the phase to be released field in the Material tab section will offer a choice of release phases. For the line rupture, a vapour release from the top of the vessel, or a liquid release from the bottom. By default, this will be set to liquid. Which is the value set for the phase field in the Materials tab section for the pressure vessel, and for this scenario you should leave the field with the default values. So on the Short Pipe tab section, this contains details for the modelling of frictional losses. Leave the pipe roughness with the default value taken for parameters, and leave the number of valves as 0. There is one bend in the 9 meters of pipework, so you should set the frequency of bend to 0.11. We'll now move to the time-varying release tab section. For newly inserted time-varying scenarios, the method for calculating the average rate is set to average between 2 times, with the time set to 0 seconds and 20 seconds. Leave the tab section with these values. You'll perform an initial run of the discharge calculations, then examine the results and decide on the most appropriate way to represent the behaviour for the rest of the consequence analysis, which may involve changing these settings. This completes the input data for this stage, and you can click on OK on the input dialog. We will now supply the tank shape data for the pressure vessel. The settings described above will complete the mandatory input data for the scenario, but when you close the dialog, you will find that scenario is still shown as incomplete in the study tree. So if you hover the mouse over this symbol, you will find that a tooltip appears saying that the tank shape is missing. The tank shape field is actually part of the input data for the pressure vessel, and it becomes mandatory if you have any time-varying scenario present under the vessel. So we should therefore open the input dialog for the pressure vessel again. You'll find that the time-varying release tab section is shown as incomplete. So move to this section and set the tank type to spherical and the tank diameter to 6.74 meters. The program will use the process and inventory data from the materials tab to calculate the vapor and liquid content of the vessel and display the results in the inventory data section at the bottom of the tab section. Click on OK on the input dialog. A message will appear warning you that the changes in the input data will make the results of the catastrophic rupture scenario out of date. Click on OK to proceed with the changes and return to the study tree. You will now find that both the pressure vessel and the time-varying scenario are now shown as complete. We will now run the discharge calculations. So select the time-varying scenario and then select Run Discharge Only from the home section of the ribbon bar. This will run the discharge calculations alone without performing the dispersion and effect calculations. The calculations may take several minutes depending on the speed of your machine. When the results are complete, view the reports and move to the TV Discharge tab. The report shows that the rate drops by less than 3% in 2 hours of release, which means that the time-varying behaviour can be ignored for this release. Time-varying discharge calculations are time-consuming, and the analysis will be easier to work with if you bypass the time-varying discharge modelling for this hazardous event. There are two possibilities in this situation. Firstly, you can use the average discharge results to create a user-defined source scenario. So most scenarios for a pressure vessel perform inbuilt discharge calculations to determine the state of the material after expansion to atmospheric pressure, which is the state required for the start of the dispersion calculations. However, the user-defined source scenario is also available. This scenario does not perform discharge calculations, but instead allows you to specify directly the state of the material. There is a separate create source option for each weather for which you perform the discharge calculation. For this scenario, the results will be the same for all weathers, and when you select the weather, the program will create a user-defined source scenario with the name user-defined source for category 1.5F. The dialog for the user-defined source scenario does not include the short pipe or time-varying release tab sections, and instead of containing fields for the pipe diameter and length, the scenario tab section contains a release segment. As shown, in which you specify the discharge rate and conditions directly. Since the user-defined source scenario does not perform any discharge modelling itself, the scenario will be created with discharge data taken from the average results for the time-varying scenario, but you can edit these values if you choose. The second option is to insert a short pipe scenario and set up the equivalent input data. The short pipe scenario models the same type of hazardous event as the time-varying short pipe scenario, but it calculates the initial discharge rate without performing any time-varying discharge modelling. Inserting this scenario involves repeating some of the data input, but this is the approach that we will take. This will make the analysis clearer and easier to maintain. If you need to change some aspect of the input data, you can edit this scenario and rerun the calculations, whereas if you use a user-defined release scenario, you would have to edit and rerun the time-varying scenario first, then create a new user-defined release scenario and delete the previous user-defined release scenario. Before you insert the short pipe scenario, rename the time varying scenario to add time varying not needed. Now right click on this time varying scenario and select the option Exclude from Calculations. The scenario will become greyed in the tree and will not be included if you run the calculation for the pressure vessel or study, which will make the calculations quicker. Next, after inserting the short pipe scenario, name it Lime Rupture Liquid. And then edit the values as follows. By opening the input dialog, set the scenario type to lime rupture, the pipe diameter to 25.4 millimeters, the pipe length to 9 meters, the elevation to 0.1 meters, and then move to the Materials tab. Set the phase to be released to liquid, and in the Short Pipe tab, set the frequency of bend in the pipe to 0.11 and OK the dialog. We will now run the consequence calculations and view the results. So firstly, select the scenario and select Run from the Home tab of the ribbon bar. When the calculations are complete, view the graphs for all the weathers. You will see that there is now a Pool Vaporization tab in the graph view, which means that the liquid in the release did rain out. If you view the reports and look at the commentary report, you will see that the rain out fraction is around 0.7 for all three weathers. So the formation and behaviour of the pool will have an effect on the dispersion or toxic effects. Moving back to the graphs, in the toxic lethality graph, the greatest effect distance is for the f1.5 meter per second weather outdoors, with a distance of 900 meters to a lethality level of 10%, which is approximately a third of the distance reached by the catastrophic rupture. The least stable condition, d5 meters per second, reaches only 300 meters for a 10% lethality outdoors. If you open the GIS results view for all three weathers and view the toxic outdoor lethality footprint for 10% lethality, you will see that the effects did not reach the village or the town. We will now define the third scenario, a toxic vapour from pipework. The vapour release is a rupture of a 2-inch pipe attached to the top of the sphere. The line runs 3.4 meters horizontally, then vertically downwards, and the rupture is assumed to occur 1 meter from the ground. So firstly, we must create the scenario as a copy of the lime rupture liquid scenario. And we'll rename this scenario as lime rupture vapour. We'll now open the dialog to alter the input data. So firstly, under the Scenario tab, set the pipe diameter to 50.8 millimeters. Set the pipe length to 13 meters. Set the elevation to 1 meter. And the outdoor release direction to down impinging on the ground. In the Materials tab, change the phase to be released to vapor. And in the Short Pipe tab, set the frequency of bend to 0.08 per meter. Now click OK to close this dialog, and we will run the consequence calculations and view the results. We'll open the GIS view to view the results and select all weathers. And from this you can see that the release rate from the 2-inch vapor line is similar to that from the 1-inch liquid line, and the two pipework releases give very similar effect distances. So we will now define 3 flammable releases. There is a propane sphere at the far north of the site. The propane sphere has the same dimensions as the chlorine sphere and the same design of pipework, and is also operating under saturated conditions at atmospheric temperature. So to set the input data for this sphere, we can define it in the equipment item and all of the scenarios by copying the chlorine equipment item and its scenarios. We will rename the vessel propane saturated 10 degrees C. So we'll now open the input dialog for the pressure vessel and change the selection of material field from chlorine to propane. After you make the selection, there will be a brief pause while the program calculates saturated pressure at 10 degrees C and also the mass of the inventory, and then display the changed values in the dialog. Now we'll move to the Dispersion tab. When you move to the Dispersion tab, you'll see that the toxic averaging time is no longer set for the averaging time for concentration of interest, and that this field is now shown as unset and mandatory. The material is flammable only, so toxic averaging time is no longer included in the list. And the program is prompting you to make a different selection for the calculation. For a flammable release, you would not want to calculate the concentration to a value as low as 100 ppm, since the cloud will not pose a hazard once it is diluted below the lower flammable limit of 2%, or 20,000 ppm. You could set a concentration yourself, but for a flammable release you can also leave the concentration of interest blank, and the program will automatically stop dispersion calculations once concentration has reached a given fraction of the LFL calculated with the flammable averaging time. Delete the value in the concentration field, and when you do this, the averaging time field will become disabled, so you do not have to supply an averaging time if there is no concentration specified. We will now change the coordinates in the Geometry tab by setting the eastern coordinate to 197,327 and the northern coordinate to 435,681. After changing each value, you should press enter to commit the change in the value. If you move to the fireball, jet fire or pool fire tab sections, you will see that 3 levels of radiation intensity are specified, but the calculation for radiation dose, probit and lethality are all unselected. These calculations are not selected by default because they can be time consuming, so you would normally only select them if you know that you need them for a particular analysis or a particular equipment item or scenario. For this tutorial, set the calculate lethality option box to on, and then set the number of input radiation levels to 5, and you can see the lethality level option in the table has become enabled. Now we will want to reset these values, so the first value be set to 0.01, second to 0.1, the third value we'll set to 0.2, the fourth value will be set to 0.5, and the fifth value will be set to 1. Now repeat this step in the Jetfire tab section and then the Pullfire tab section, and click OK on the dialog. We will now run the consequence calculations and view the results for this pressure vessel. So select the propane equipment node and use the run option to run the calculations for all three scenarios. You can view the results for all three scenarios at the same time, as long as you view results for the same single weather for all the scenarios. To do this, move to the Weathers tab of the study tree, select the category 1.5F weather, and then click on the Graphs option. A select dialog will appear showing all of the nodes in the Model tab section, and you can check the box next to the propane saturated 10 degrees C folder and click on OK. When you click on OK, the Graphs view will open. The Graphs view will contain tab sections for concentration graphs as well as for toxic models, but it will also contain Jetfire, Fireball, Pullfire, Explosion and Flashfire tab sections instead of the Toxic tab section. The main features of the graphs are now defined. Firstly, for the Jetfire graph, the Jetfire tab section contains three graphs which are presenting results for the two pipework failures. The first graph shows radiation level versus distance. The second shows intensity radii to the lowest of the three default radiation levels set in the input data. And the third graph shows the lethality radii to a lethality level of 1%, which is the lowest of the 5 lethality levels that you set. The maximum downwind effect distance shown in these graphs is around 32 meters, which is the distance for 4 kilowatts per meter squared for the liquid line rupture release. If a given fire radii graph is showing results for more than one scenario or more than one weather, then it will initially only be displaying results for a single level, which will be the lowest level set for that type of result. This is different from a graph for a single scenario and weather, which will initially always display results for all available levels. To see the results for additional fire radii levels, you can click on Series in the Configuration tab of the ribbon bar to open the Edit Series Properties dialog. This dialog lists each of the available level results for each scenario, and you can check the boxes for additional levels to include them in the graph. So we will now look at the Pullfire graphs. There are two sets of Pullfire graph. There's the early Pullfire and the late Pullfire. The early Pullfire is modelled for a continuous release only and occurs at the beginning of the release at the time when the spill rate into the pool equals the fire burn rate. The Pullfire graphs are showing results only for the liquid line rupture release, as this is the only scenario that gives rain out, and this means that the two radii graphs will initially be showing results for more than one level. The maximum downwind effect distance is about 28 meters to a radiation level of 4 kilowatts per meter squared for the late Pullfire, and the distance to a lethality level of 1% of about 21 meters. We'll now look at the Fireball graphs. The Fireball tab section also contains three graphs. These are showing results only for the rupture, and this means that the two radii graphs will initially be showing results for more than one level, as shown. The maximum downwind effect distance is about 600 meters to a radiation level of 4 kilowatts per meter squared, and the distance to a lethality level of 1% is about 290 meters. There is no ellipse for a lethality level of 100% because the Fireball does not produce the necessary radiation dose at the height of interest. We'll now look at the explosion graphs. The two early explosion graphs contain results only for the rupture, since immediate explosions are assumed not to occur for continuous releases. However, the late explosion graphs contain results for all three scenarios. The late explosion worst case graph shows the effect radii for the explosion time, which gives the greatest downwind distance for the lowest overpressure, set in the parameters, and the legend for the late explosion time graph gives the time at which the worst case explosion occurs. The greatest downwind effect distance is about 1,150 meters for the rupture, and it occurs at 9.3 seconds. The flashfire graph shows the zone for the cloud at the time that it covers the maximum area. For the rupture, this gives a maximum downwind effect distance of 400 meters to 10,000 ppm, whereas for the two pipework releases, this gives a distance of about 70 meters to the same concentration. 10,000 ppm is 50% of the LFL, which is the fraction set by default in the flammable parameters as the boundary of the flashfire effect zone. We will now look at alternative methods for modelling early explosions. When you were setting the input data for the flammable scenario, you left the flammable tab section with the default settings, which means that the early explosion for the rupture scenario was modelled with the default method, which is the TNT method. In this section, you will create a version of the rupture scenario that uses the other methods for modelling early explosions and compare them. So firstly, we need to create a folder and scenario for the other methods. So insert a folder under the propane equipment node using the right click menu and then go into insert folder. We will name this folder early explosion method. We'll select and copy the rupture scenario from the propane vessel and then select the folder and use paste 3 times to create 3 copies of the catastrophic rupture. Once we have inserted the 3 copies into the early explosion methods folder, they should be renamed TNT Groundburst, Multi-Energy and Baker Strelo Tang. We will now edit the information for TNT Groundburst by opening the input dialog. Move to the explosion parameter tab to check the input data for the modelling. You can leave the explosion efficiency with the default values, but for this scenario you should set the location to groundburst. This means that you are assuming that the explosion is sufficiently close to the ground that there will be reflection effects in the pressure wave. We'll now click on OK to close the input dialog. For the multi-energy catastrophic rupture, you'll open the input dialog and move to the Flammables tab and choose multi-energy for the explosion method field. A multi-energy tab section will appear in the dialog, and you use this tab section to define up to 7 regions of confinement within the cloud, and also specify the strength of an explosion in an unconfined region of the cloud. By default, the number of confined is set to 0, which means that there are no mandatory fields in the tab section, and that the scenario will run even if you do not set any values in the tab section. But it also means that by default, the scenario will not produce any explosion results. We will now change the input data as follows. We will change the model unconfined volume as explosion source to use unconfined strength. We will change the blast strength, which is now enabled, to 2. And we will use fraction. And the number of confined sources will be changed to 3. The strength of confinement will be set to 8, 7 and 6. And the volume fraction will be set to 0.3 for each. This means that for the tutorial, you will define 3 regions of confinement that each occupy 30% of the volume of the cloud, and with a range of confinement strengths between 6 and 8. We'll now click on OK to close the dialog. We will now open the dialog for the Baker-Strahel-Tang and move to the Flammable tab. Choose the Baker-Strahel-Tang for the explosion method field, and the Baker-Strahel-Tang tab will now become available. For this tutorial, you will not use the default options to supply a value for the speed of the flame, and instead you will have the program calculate the speed of the flame with other inputs. So firstly, the Mach number supplied should be unticked. The flame explosion should be set to 2. The obstacle density set to medium, and the fuel reactivity also set to medium. With the correlation for the ground effect set to 1.6, and the confined volume set to 500. The release is relatively close to the ground, and there is likely to be some reflection of the pressure waves off the ground, and that is why the correction for the ground effect should be set to 1.6. So you click on OK to accept this dialog, and we will now run the calculation for this folder and view the results. We will now view the graph for the 1.5 F weather. Select the 1.5 F weather, select graph from the ribbon. Select the early explosion method folder to view the graph. If we move to the explosions tab and then look at the early explosion distance graph, we'll initially see that the Baker-Strahel-Tang scenario is given the highest peak overpressure of about 1.02 bar with respect to the other 2 methods, with the pressure declining rapidly with distance, with no effects beyond around 300 meters. The TNT ground burst scenario produces a peak pressure of 1 bar, and the pressure declines less rapidly with distance, so the pressure at 300 meters is 0.2, and there are effects out to around 1,400 meters. For the multi-energy scenario, the graph initially shows the results for the unconfined region of the cloud. We will now look at flammable releases from a rail tank wagon. The propane is delivered to the facility by tank wagon from a marshalling yard 10 kilometers to the north. The deliveries take place once a week, involving 2 tank wagons, and are always during the day and never at night. The wagons are 10.6 meters in length, 2.6 meters in diameter, with a volume of 54 meters cubed. They're raised 0.5 meters above the ground and are delivered with a fill level of 80%. The propane is under the same condition as in the sphere, under saturated conditions at atmospheric temperature. There are many hazardous events that could be modelled for the tank wagon, including leaks during the unloading process. This tutorial will consider only the rupture of a wagon under normal operating conditions, a leak from the liquid side of the wagon, and a fireball produced by catastrophic rupture of a wagon under flame impingement. All events are assumed to occur while the wagons are at the up unloading point 100 meters south of the propane sphere. So firstly, we need to define a folder and create the equipment data. So we want to insert a folder under the study tree. And name this folder Tank Wagons. Create a copy of the propane saturated 10 degrees C pressure vessel in Tank Wagon folder, and open the dialog for the pressure vessel and change the volume inventory to 43.2 and the geometry northern coordinate to 435,581 and OK the dialog. We will then edit the rupture scenario and change the elevation to 1.8 meters. And OK the dialog. We now need to define the leak from the liquid side of the wagon. So firstly, we insert a leak scenario under the equipment node. And name it 1 inch liquid. For release from the body of a vessel rather than from attached pipework, you should use a leak scenario. It will give a larger discharge rate than a short pipe scenario, since there are no frictional losses during the flow to the leak location. The leak is assumed to be at the top of the tank, which is the most conservative assumption for the tank head and the duration. So we edit the scenario and change the data as follows. So the orifice diameter we would like to change to 25.4 centimeters. The tank head should be changed to 1.95 meters. The elevation should be changed to 0.5 meters. And the outdoor release direction should be changed to down, impinging on the ground. We can now OK the dialog. We would also like to define a fireball failure under flame impingement. The program allows you to model immediate ignition effects from fireballs and pool fires on their own, separated from any modelling of dispersion and delayed ignition effects, and you do this by using the fireball scenario or pool fire scenario under a standalone equipment item, rather than one of the discharge scenarios under the pressure vessel or atmospheric storage tank item. So firstly, to define a standalone equipment, select the tank wagon folder, then select the option to insert a standalone. The GIS input view will become selected, and you should click on the map somewhere next to the dot for the tank wagon pressure vessel item. You will adjust the location as necessary in the next step. Name the standalone item propane wagon. And open the input dialog. For the material, select propane. And for the geometry, set the eastern coordinate to 197,327 and the northern coordinate to 435,581. And OK the dialog. We now need to define a fireball scenario. Under the standalone node, insert a fireball scenario and name it fireball under flame impingement. Open the input dialog for the fireball scenario and set the data as follows. Set the release mass to 22.2 times 10 to the 3. Set the vapor mass to 0.25. Check the supply burst pressure tick box and set the burst pressure to 8.57. In the radiation calculation tab, tick the radiation versus distance box and the radiation ellipse box. Within the radiation versus distance tab, set the maximum distance to 500 meters and the angle from release direction to 0 degrees and the height above origin to 0 also. In the radiation ellipse tab, set the ellipse type required to incident radiation and the specified radiation intensity to 4 kilowatts per meter squared. The burst pressure is 60% greater than the normal operating pressure and is used in calculating the surface emissive power of the fireball. The fireball tab section gives you the choice between using a correlation to obtain radius, duration and emissive power, or entering your own values. For this scenario, you are using the correlation. OK the dialog and run the calculation for the tank wagon. Move to the Weathers tab and view the graph for the 1.5F weather. Select the tank wagon folder. In the Fireball tab, move to the Intensity Radii folder, and from this you can see that the Fireball scenario gives slightly larger effect distances than the Rupture scenario, with a distance of around 460 meters to 4 kilowatts per meter squared, compared with 435. This shows the effect of the higher vessel pressure used in the fire scenario to model failure under flame impingement, whereas the Rupture scenario considers a rupture under normal operating conditions, which then has a probability of igniting immediately and giving fireball effects. You have now completed the tutorial, and you should save the workspace in order to save changes you have made. This tutorial has not covered every feature of the program, but you should now have enough of an understanding of the approach and methods used in the program to be able to explore the remaining features yourself, with the assistance of the online help. The topics under commonly used features in the Contents tab of the Help window give quick access to details of all the main features, and you can also use the Index and Search tabs to find help on a particular topic. If you need further details on any aspect of the program, or if you need guidance on how to model a particular situation for your facility, you should contact software support using the details given in the Help tab of the ribbon bar.